box you like the big.
Thanks.
What?
Are we allowed to talk right now?
Ask Mike.
Ready? Okay, great. So for the final talk before lunch, we have Sumegha Garg here to tell us about online Omniprediction. Sumegha's did her PhD at Princeton, is now doing did a postdoc at Harvard. No, but what's it called? The Raman Fellowship. Is that now at Stanford doing a postdoc and is heading to Rutgers next year.
Thank you, organizers, for inviting me to give a talk. I'm Sumegha, and I'll talk about a recent joint work with Chris, Omar, and Aaron. So this is still a work in progress, and we plan to put it online in a couple of weeks. If you have any questions about more technical details, email us or catch Chris or Omar. So my talk, so we will talk about online setting and Omni prediction. So my talk might be a convex combination of like Parikshit's talk and Dean's talk, but it's optimized for this new concept. So we have a new paper. And okay, let's start. So Omni prediction is, as we saw in Parikshit's talk yesterday, the goal of Omni prediction is to output a single predictor that can be used for loss minimization for multiple losses simultaneously. And loss minimization is a very widely used paradigm in machine learning. Very briefly, in the batch setting, what loss minimization asks is as follows. So you are given, you have samples from a distribution D, which the distribution is over the feature variables and the labels, where we are assuming that labels are binary variables. And then you are given a class of hypothesis, capital F. And then the goal is to minimize your expected loss, where expected loss is defined as there is a loss function L, and you want to minimize the loss between the loss that the function f of x has with respect to the labels y. And now, what is this minimization over? It is over this concept class capital F. So this is the loss minimization paradigm. You want to minimize this loss over this, optimize the loss over this class of hypothesis. And you can ask this question for different classes of hypothesis for different loss functions. For example, the very common loss functions used are the squared loss function or the exponential loss function. And as we saw in Parikshit's talk, different loss functions will be optimized by different functions, small f in class capital F. So this is what I will say about the formal setting of loss minimization. And now, what is the goal of Omni prediction? Our first attempt is that you want to output a single predictor P that optimizes the loss compared to this class capital F for all losses in this class capital L. So we can think of capital L as, in this talk, we will think of it as like Lipschitz convex functions. So for all Lipschitz convex functions, is there a predictor P? You know what is the class capital F beforehand. Is there a single predictor P that optimizes the losses for all the losses L when compared to this comparative class? As we saw in Parikshit's talk yesterday, even if P of X is the base optimal predictor, let's say it's expectation of Y given X, then also you might not want to input P of X into L for all losses. So for example, if the loss is squared loss, then this is minimized at P of X is equal to expectation of Y given X. But if the loss is like modulus loss, where you are doing Y minus P, mod of Y minus P of X, then you want to round P of X to 0 or 1. So then the definition of Omni prediction is you can do some simple pre-processing on your predictions such that you get a minimizer for that loss. So for every loss in this class capital L, this expected loss is minimized when you do appropriate post-processing on a single predictor P. And when I say minimized, you are comparing this loss with respect to the minimum loss that a function F in this capital class F which receives. Okay, any questions till now? So this is the Omni prediction was defined a couple of years ago, and and Parikshit already told us about this, and he told us that how to achieve Omni prediction through the concept of multi-calibration, which was defined like 5 years ago now. So very briefly, multi-calibration with respect to a class capital F wants us that conditioned on a prediction value V, for any function F in that class capital F, Fx should not be correlated with Y minus V. This was first studied as a fairness notion, and the idea is that, for example, a sensitive attribute should not be correlated with underscoring. And then the paper on Omni predictor proved that if a predictor P is multi-calibrated with respect to a class capital F, then it is Omni predictor for all Lipschitz convex losses for the class of hypothesis capital F. So this is all in the batch setting. So this paper, all the papers I have talked right now about the Omni predictor paper and the multi-calibration paper are in the batch setting. And then our contribution is we extend to the distribution-free online setting, which has very natural motivations. For example, weather predictions. We use weather predictions every day, and these are the predictions that are made in online setting. I don't know, Siri is trying to figure out what is the probability of rain every day. So what's the goal of online Omni prediction then? We want to find one predictor that simultaneously achieves low regret for multiple losses. So for the batch setting, we wanted to minimize the loss, but in the online setting, perfect loss minimization is just not possible because you don't like it. In the offline setting, you can see the entire data, but in the online setting, you're not able to see it. So you usually in the online setting, you talk about low regret algorithms where you want low regret. So now here, similarly, instead of thing like getting perfect loss minimization, we want one predictor, online predictor that simultaneously achieves low regret for multiple losses. And the running example that we will have in this talk is the example of forecasting, that is like forecasting weather predictions, making predictions on what is the probability of rain. And so from now onwards, I will call the predictor as a forecaster, so that we know that we are in the online setting. Okay, so that's our goal. To achieve this goal, we again work with online multi-calibration, and on the way one of our technical contributions is a new Oracle efficient online multi-calibration algorithm. I will touch upon this algorithm very briefly during the end of my talk. And finally, I think this new study of online Omni prediction opens up a lot of interesting questions about regret rates that I want to convince you and like to work on more after this talk. Okay, so what's the motivation for studying online Omni prediction? It's very natural. So we all use weather predictions. There's a forecaster that predicts probability of rain each day, which is used by multiple agents to make decisions. For example, there might be a farmer who wants to figure out whether they want to plant their seeds today or not. There might be a fisherwoman who wants to see whether she should go fish today or not. And then there might be people like us who are just deciding whether to go to office or not. So this, so there are high stake, low stake. Many people might have high or low stakes in the predictions of low rain. So they might have, different agents have different objective functions, which we call different loss objectives that they're optimizing for. But they don't want to run an online regret algorithm per agent. So you want to use these predictions and do some simple post-processing and still get some low regret algorithm. So this is the motivation for studying online Omni prediction. Again, so we want to achieve our way of achieving online Omni prediction is through online multi-calibration. So let's look at what is known about calibration in the online setting. And the calibrated forecast was defined in a paper of David's paper in 1985. Yeah.
Sorry, for the agents, should I think of them as having different like utilities or something? Like, why does the same prediction not work for every agent?
No, we want the same prediction, but they might have different loss functions. So, for example, one loss function might have different weighting on false positive and false negative.
And that's like their utility. Okay, thanks.
Okay, so this was defined in this. So as Dean told us that calibration is usually thought of as a post-processing, that what could we have done, but we are in the online setting, we cannot do post-processing. We have to make decisions online. So it's not even clear that whether calibrated forecasts can exist. So there is a paper that I'm sorry that I didn't cite, which said that deterministic calibrated forecasters cannot exist. And then there's multiple works and that showed that existence of calibrated forecasters if your forecasters are randomized. These papers go through a min-max argument, as we saw in Dean's talk. I don't cite Hart's personal communication because I don't know, I was 2 years old then. Okay, so this is the so all of these papers go through a min-max argument. Either you can go through a min-max argument over the entire time sequence or at every time step, and these give you different algorithms, existence or explicit constructions for calibrated forecasters. The point about min-max arguments is that they are not efficient, and we want to get around the min-max arguments, and that is what we are trying to do in this paper. So I will briefly talk about this the paper by Gupta et al. When we talk about Oracle efficient algorithms. Okay, so this is about calibration. What about loss minimization in the online setting? So there are various notions of, so what we are trying to do is, in general, like we are trying to optimize a lot of different objectives at the same time, right? So there are various notions of regret in the online adversarial setting that optimizes for several objective functions simultaneously. For example, you can look at the sleeping expert setting, adaptive regret setting, swap regret setting. So these all, for example, adaptive regret is like you want to have low regret for every consecutive batch of time steps. So all these algorithms are looking at are seeking to minimize the same loss function over different subsequences of time steps. What we are trying to do is we want to optimize for different loss functions over the entire sequence of time steps. So this is if you're trying to put our work of online Omni prediction into this setting of online adversary setting of like different objectives. Okay. So this is all about like motivation related work. From now onwards, I will start talking about like how to achieve online Omni prediction. So does anyone have any questions?
What is the definition of online Omni prediction?
We will get to it. Any other questions? Okay, so this is the, thanks Michael for that question. So this is the formal online setting. We have at the tth time step, adversary chooses a feature comma label pair. A forecaster only sees the feature vector, and after seeing the feature vector, they make a prediction PT and forecast PT. And then after it makes this prediction, it sees the label YT. And then there is a third agent, which is a learner with loss L belonging to this capital class L. And what they do is they use a simple post-processing function to choose an action at the tth time step. And so AT, the action at the tth time step for loss L is given by K of L, which is the optimal post-processing function for L of the prediction made by the forecaster PT. Forecaster does not know what is the learner's loss function, but it just knows that it is coming from this class of capital L. And then, this is a learner, and then what is the regret that this learner sees? So the regret is defined as with respect to the comparator class capital F. So you look at all the time steps in the end, and then see what action should I have taken, which function from this hypothesis class capital F would have minimized my loss. And you want to have low regret with respect to this minimizer. So this is the loss that you experience. AT is your action at each time step, and the loss is loss of YT comma AT. And this loss should be small compared to the minimum loss in F of F in capital F. So this is the regret. There should be if action ATs are randomized, so there would be an expected regret definition. But for the talk, I'm ignoring the expectations. Okay. Yeah.
So that's good. So the learner chooses the loss at the end, knowing after seeing also all the actual actions. Then,
no,
if they're
no, learner's loss is defined before. So it's for every it's fixed for every time step, and it's defined for beforehand. I agree that in the online setting, usually you can choose a different loss function for every time step.
No, I understand it's a single one, but
yeah.
What's order of quantifiers, right? It's only the losses chosen
for all L. So yeah. So let me tell you the quantifiers and then yeah. Okay. So what is AT? AT is the processing function. So we want that. So this is the regret for the learner, which has loss cap L. And then what is the definition of online Omni prediction? We want that for all L in this class capital L, this regret should be something like 1 by T to the alpha. So usually, so as I said, we cannot get perfect loss minimization, but usually we want like sublinear regret such that alpha is like strictly less than 1. So that when T goes to infinity, you are getting perfect loss minimization. So usually like in the online setting, you want sublinear regret. And this is the definition of Omni prediction. Okay. Any questions?
So if so just by the original Omnipredictor paper, if your sequence of predictions is multi-calibrated, then this should give you a convex Omnipredictor, yes?
Yes. There are some nuances that we will
Because
talk
of the
about.
randomization.
No, because of like what is the exact definition of multi-calibration we're using. We'll see. So
And I guess sort of another natural candidate definition of what an Omni predictor in the online setting would be is that the along with sort of the X, you're seeing loss at every step. And you're given a lot. There's a single decision maker. They can be given any loss from this class, and they have to make that decision. And I guess it is similar, but if you only get the loss as feedback instead of the outcome, then maybe you're hosed.
I didn't know this actually.
So your forecaster is seeing Y as feedback. They're not just observing a loss.
Yeah. That's the definition of Omni prediction. Yeah, we can let's start in the.
Yeah.
Okay. So for very nice convex problems with nice loss minimization problems with nice convex properties, you can usually get 1 by square root t regret and then so the question is like, what are the regret rates that we can get for Omni prediction? And this is, I think I find it very interesting. What are the lower bounds and upper bounds for these regret rates? And we will see them. Okay, so again, so we go through multi-calibration. Let's recall what is a calibration error. So a calibration error for a prediction value V is the expectation of yt minus V on the days, conditioned on the days that you predicted V. So in the online setting, you cannot get calibration error to be 0. So we will actually talk about like in terms of errors and not in terms of like what calibration. So okay, and then multi-calibration is you add an F in this error and you look at the expectation correlation between yt minus V and Fx. And then the thing is that there are various different multi-calibration definitions which are all used interchangeably for the batch setting, but it becomes important to understand the nuances of these definitions for the online setting to figure out like what are the rates that we are getting for Omni prediction. So L infinity multi-calibration is you take max over V, the fraction of the times you predicted value V times the error of F comma V. And you want this to be small. And for this L infinity multi-calibration to make sense, to be non-trivial, you really need to care about like what is small compared to what is the discretization of PT. So I won't go into those details. But then the second is L1 multi-calibration, where you sum over these values for V. So it is expectation over V, absolute value of this error term. And this L1 multi-calibration, it makes sense to understand this for every small parameter because it is non-trivial to achieve small L1 multi-calibration. And then the last definition of multi-calibration that I want to look at is L2 multi-calibration, which does expectation over V, error of F comma V square. And what previous paper on this nice online multi-calibration gave us is L infinity multi-calibration. They gave us an L infinity multi-calibration with error rate of 1 by square root t. But there is a log of a capital F factor, which means that their algorithm only works for finite hypothesis classes, and they get L infinity multi-calibration. So now this does give an L1 multi-calibration after you do some post processing on their algorithm. So which tells us that you can get L1 online multi-calibration with the rate of 1/t⁴ for finite sized hypothesis classes. And as in the batch case also uses L1 multi-calibration. As in the batch case, we can get online Omni prediction for Lipschitz convex losses through this through reduction to online L1 multi-calibration. So this means that doing some massaging over previous works, we can get a 1/t⁴ rate for regret rate for online Omni prediction for finite hypothesis classes. And then the question is, what about real valued hypothesis classes where the size of f can be infinite? And then the second question is, can we get better rate? Now this question is very interesting because there is a lower bound by Mingda and Garg that showed that on for L1 calibration, you cannot get a better than 1/t⁴ bound. So this means that if we want to get online Omni prediction through L1 online multi-calibration, then we cannot get we cannot get 1/√t regret that we get for loss minimizations for many problems. Okay, great. We don't get better rates, but we make progress on this question about like getting online multi-calibration and online Omni prediction for infinite sized hypothesis classes. Oh. Okay. So how we do it is we go through, instead of developing algorithms for L infinity, we develop algorithms for L2 multi-calibration. And this is an algorithm that is not a min-max argument. It goes through swap regret kind guarantees. And then finally, to achieve Omni prediction from L2 multi-calibration, we still go through L1 multi-calibration. But this reduction from L2 to L1 multi-calibration is lossy. So T⁻α rate, error rate L2 multi-calibration implies T⁻α/2 L1 multi-calibration. And then this is an open problem. Can we directly get online L1 multi-calibration? We don't know. Okay. So very briefly about our L2 Oracle efficient algorithm of L2 multi-calibration. It uses this thing that in batch case, there is recent work that showed equivalence between squared loss minimization for every lever set and multi-calibration when both these optimizations are done for a hypothesis class F, which is closed under affine transformations. And for example, linear functions are satisfies this currently. And then using this equivalence, we develop a swap regret kind of algorithm to get L2 multi-calibration against F class, capital F. I won't say more about this, but the idea is that we can reduce online L2 multi-calibration to solving online squared regression, error regression problem over the class capital F. Okay. So I already told you about this, that like for finite Fs, we can get 1/2T⁴ online Omni prediction regret rates. And as this is work in progress, we are still figuring out the exact sublinear rates that we get for infinite hypothesis classes, especially linear functions. But for infinite F, we believe that the swap regret algorithm gives us sublinear regret for Omni prediction for linear functions or from other natural hypothesis classes. Next, I want to mention that last time, okay, so yesterday, Parikshit also mentioned this swap Omni prediction definition. He touched upon it very briefly. I'm not going to define it, but the point is that our algorithm also gives us swap Omni prediction. And in their paper, they showed that swap Omni prediction implies L2 multi-calibration. but we want a strong, like, because we really care about like whether it's L1 or L2 multi-calibration, to say anything about regret rates, we wanted to reduce it to L1 multi-calibration, and we can do that. So we can reduce swap Omni prediction to L1 multi-calibration and say that at least swap Omni prediction you cannot achieve but a rate of 1 by square root t. Okay. This is all for my talk. I will end with open questions. The first open question is, can we achieve Omni prediction with even for finite loss functions? Like, I'm not even asking you to give me for the entire class of Lipschitz convex losses. For finite number of loss functions, even like 2 loss functions, can we get a regret rate of 1 by square root t? Note that we need to go, remember that we shouldn't try to achieve this through L1 calibration, because there is a bound of L1 on L1 calibration. So in the current paper, I think for some subclass of loss functions, we hint at like how we can get 1 by square root t, but I wouldn't talk about that right now. And then the next question is about L1 multi-calibration. It's like, can we get an oracle efficient or even a constructive forecaster for L1 multi-calibration error rate of 1 by 2 to the 2 by 3? So why 1 by t to the 2 by 3? I think even for L1 calibration, people believe this is the lower bound. And paper by Foster and Bora gave a constructed proof for L1 calibration, but it goes through L2 calibration. So they gave that L2 calibration rate of 1 by t to the 1 by 3, and that implies an L1 calibration. So we can show these like existence proofs of L1 multi-calibration with error rate of this, but is there a constructive forecaster for? We don't know how to handle L1 multi-calibration in a constructive sense in time steps. Okay, thank you.
Any questions before we break for lunch? In the interest of time, let's thank Sumegha again and take any questions.
See if we believe
Don't worry about it. No worries. Thanks.
I feel bad about it, but I'm sort of headed out.
I remember reading this. Well, I'm kind of waiting for Russell, but I'm also gonna.
So Blackwell.
Yeah.
Sort of the way
Better than.
Yeah. Yeah, like.
So you're way from multiple.
It handles so that's kind of like what we do that
I have to work on.